Still the lightings are not that good.
Yeah,
Okay.
I told the sir also.
So
Sir said it's okay now. You manage.
one lighting, if it is directly coming from there, na, it will be good.
Yeah, that will be. Or else. Directly
You can
from-
actually also keep like that. Or you can actually put one lighting here. This one, na?
Yes.
What is this?
This is camera. Text camera.
Text camera means?
Suppose you are writing something in the board, that will capture in, and we can make as a PDF.
Oh, it's like that. But one lighting can be actually arranged here also. It's possible. Okay, let's see.
I'll tell the sir also.
Okay.
Thank you, sir.
Yeah, it's okay. Okay, in the last class we have discussed something about the adjacence of angular momentum, and this adjacence of angular momentum can be done in a two way. One is called coupled basis or in the coupled state. Coupled state. So J1 and J2, M1, J3, M3. This is actually state vector for writing the coupled state, and the set of state vector in coupled state is written J1, J2, J3, M3. And the second way we can also do it adjacence of angular momentum by uncoupled states. Uncoupled state, and these uncoupled state can be written as J1, J2, M1, M2, a state vector, and the set of state vectors is written for uncoupled state as J1, J2, M1, M2. Fine. Today, what we are going to discuss how to correlate or the connect between these two coupled and uncoupled states. So, how to convert the uncoupled state, the adjacence of angular momentum in coupled state to uncoupled state, vice versa. So, this can be done with some transformation, and the transformation can be done with help of matrix, and that matrix we call it as unitary matrix or unitary transformation. That the transformation from coupled state to uncoupled state, vice versa, we can do it by a unitary transformation. That unitary transformation is in form of a matrix. So, that is actually a square matrix, and the element of that unitary matrix, element of each and every that unitary matrix can be calculated by some selection rules, applying by selection rules, and that unitary transformation and element of that unitary transformation we call it a coefficient, CG coefficient, Clebsch Gordan coefficient. So, how to calculate that Clebsch Gordan coefficient is going to discuss now onwards. Okay. Fine. So, let us start with first the completeness condition. So, how to write the completeness condition for okay. So, let us actually write the coupled basis. So, the state vector for coupled basis is J1, J2 and J3, M3. This is a state vector, and this state vector can be written with the completeness relation. So, here I am actually putting this I, M and J1 and J2 and J3, M3 state vector, and this completeness relation comes from a uncoupled basis. This is a coupled state, and here this completeness relation we had to write it from the uncoupled basis. So this one further can be written sum over m1 equal to minus j1 to j1, so it will be plus j1, and m2 is nothing but minus j2 to plus j2, and that outer product of the uncoupled state is nothing but the completeness relation. So j1 j2 m1 m2, this is outer product, and again j1 j2 m1 m2, then this term is actually coming here, because this completeness relation im is nothing but 1, sum over this entire term is nothing but 1, so there is no harm to insert here. Then j1 and j2 j3 m3. So this value for the completeness equation here, whatever it is written, is nothing but im r is equal to 1. So there is no harm for inserting this one. When we are considering a coupled state, then the completeness relation should be a uncoupled state. If you are considering here a uncoupled state, then the completeness relation which you are going to insert here should be from the coupled basis. Fine. Next, if you look this expression, here, this expression, it's an inner product between the coupled and uncoupled basis. If you look at here, this one will give you the inner product between coupled and uncoupled. And moreover, the inner product between these two states will give you just a number only. This is nothing but a number. It's a number or the scalar quantity, number or scalar quantity. So if this is the scalar quantity, then we can write it either here or from here to here. Anywhere in this expression we can write it, but within the epsilon. So we can write it. So for rewriting this expression, sum over m1 is minus j12 plus j1, again sum over m2 minus j2 to j2, then I am bringing this inner product from here to here. So in that case, j1 j2 m1 m2, again j1 j2 j3 m3, then you keep it this term here. So j1 j2 m1 m2. If you look this expression again and compare with the first expression, okay, if you look this one, and or if you write it j1 and j2 and j3 m3, if you compare both sides of this expression, this term is there, again this term is also here, there is no problem, but additionally this one term is we are getting. This is the inner product between two numbers. Okay, this inner product between two numbers here, this term is nothing but a coefficient or the scalar quantity. Of course, it's nothing but a coefficient, and that coefficient we call it as CG coefficient. This coefficient we call it this Clebsch Gordan coefficient, CG coefficient. So this coefficient or the transformation term, okay, so transforming from a uncoupled state to coupled state, this is nothing but a uncoupled state or uncoupled basis, and this one is coupled basis. Transforming from yeah, uncoupled basis to coupled basis, there is a coefficient is required. That coefficient is called CG coefficient, and that coefficient is in the form of unitary transformation or transforming from uncoupled to coupled. So there is a transformation coefficient, and that transformation coefficient is in the form of matrix, okay, square matrix. So that matrix or the transformation, we call it as unitary transformation. Unitary transformation. Fine. So the entries of all these unitary transformation or the matrix is nothing but a real numbers. So the entries of unitary transformation or the values in the matrix is nothing but real numbers. The entries all are real numbers. Real numbers. If that is the case, if all the entries are real numbers, in the coefficient, in the CG coefficient, sum over this is nothing but the coefficient, CG coefficient, and it's a scalar quantity or the real numbers. The entries of this matrix is nothing but real numbers. If that is the case, then if it is a real number, then we can actually write it instead of ket bracket, we can actually interchange in this way. There is no harm, only I am writing this term. This one can be interchanged. So how it is interchanged? J1 J2 and J3 M3 is J1 and J2 M1 M2 is nothing but J1 and J2 M1 M2 J1 J2 J3 M3. It's both are same. Okay. So by keeping this in our mind, we will actually start to write the orthogonality condition for writing the coupled basis. So for writing the orthogonality condition for writing orthogonality condition using a coupled basis. Coupled basis. So J1 and J2 coupled basis. So J3 M3 J1 J2 J3 M3 dash. This will give you the orthogonality condition. So further, this can be written according to a Kronker delta function. We can write it. So this is J1 and J1. We can write it delta J1 and J1, and we can actually complete this two term. So delta J2 and J2, and for writing this two, delta J1 dash J3 dash and J3, and this last term delta M3 dash M3. Fine. So the delta I J1 and J1 and delta J2 J2, this term will be 1. This cannot be actually 1 at this moment. So further we can write it this as delta J3 dash and J3, again delta M3 dash M3 is nothing but this value. Now if you are inserting the completeness relation or equation here in between this, so how to write it? I am writing. So J1 and J2 and J3 dash M3 dash, here I am putting this completeness value because that is nothing but 1. Okay, this value is nothing but 1. So then J1 and J2 J3 M3 is equal to delta J3 dash J3 delta M3 dash M3. Fine. So we are using already the coupled basis. So this completeness relation has to be written in the form of uncoupled basis. Our aim is to transform a coupled basis to uncoupled or uncoupled basis to coupled basis. If you are considering orthogonality condition with the coupled basis, then this completeness relation which you are going to insert here, it should be uncoupled basis. If you are taking the orthogonality condition with the uncoupled basis, suppose example, in that case the completeness relation which you are going to insert it here should be a coupled basis. Okay. Now let it write J1 and J2 J3 dash M3 dash, here I M, it should be a uncoupled basis. So sum over M1 minus J1 to J1 and sum over M2 minus J2 to J2, then this is nothing but completeness relation is outer product between the two uncoupled bases. So in that case, so J1 J2 M1 M2 and J1 J2 M1 M2. Then after that we have to write this term. So J1 J2 J3 M3, this is nothing but delta J3 dash J3, again delta M3 dash M3. So on the other hand, we can actually write this sum over instead of writing here, because this is nothing but a number. Okay, so we can actually put this sum over, we can put outside because it's a common, the m value varies from minus J1 to J2, so we can keep it outside, there is no problem. So for rewriting this again, M1 minus J1 to J1 and M2 minus J2 to J2, then you bring it inside. So J1 J2 J3 dash M3 dash J1 J2 M1 M2, I am writing this two term here. Then the remaining term I am continuing M1 M2 J1 J2 J3 M3 is nothing but delta J3 dash J3 and delta M3 dash M3. Fine. But according to the unitary transformation, just now we have written it, that inner product between Z1, Z2, M1, M2 and Z1, Z2, Z3, M3 can be written because it's a number. So one we can write it Z1, Z2, Z3, M3, Z1, Z2, M1, M2. There is no harm for writing this because it's a scalar quantity, it's a number. So inner product between these two quantity will give you same as inner product between these two quantity. So there is no problem. So in that case, if we are keeping this in our mind, we can also rewrite this term here, whatever it is written, this term can be interchanged, the states can be interchanged. So if we are writing the states with interchanging, then again sum over M1 minus J1 to Z1 and sum over M2 minus J2 to Z2, then J1 and Z2, this term is coming first, M1, M2, then J1, Z2 and Z3 dash, M3 dash. So this term is coming here. So that means bracket is interchanged. Then this term J1 and J2, M1, M2, here J1, J2, Z3, M3 is nothing but delta J3 dash, J3, delta M3 dash, M3. Fine. Now if we are implying a condition that if J3 is equal to J3 dash or J3 dash is equal to J3, then the value of M3 dash is also M3. If that is the condition, if we are applying here, then what we will get it, sum over M1 equal to minus J1 to J1 minus J1 to plus J1 and sum over M2 equal to minus J2 plus J2, then this term J1, J2, then M1, M2, J1, J2, here it will be J3, M3. Then again another term is there, so we will get it, this one is equal to delta J3 and J3 delta M3 M3. So this term, this is also 1 and this is also 1, so it is nothing but 1. So this is the condition for normality. So now we will get it, condition for normality. Okay. In such a way, we can also move from uncoupled basis to coupled basis, transforming a uncoupled state to coupled state for transforming uncoupled state to or basis to coupled state. For that, first we had to take it the orthogonality condition with the uncoupled state. Okay, so take the orthogonality condition with uncoupled state. So what is the orthogonality condition of uncoupled state? You take it J1, J2, M1, M2, J1, J2, M1, M2. Here it is actually the states are different. And this one is equal to, so this is a delta J1, again J1, this two term if you are combining, and if you are combining this two term again delta J2 and J2, and when you combine these two states, so M1 dash M1 and M2 dash M2. Again these values are 1. So finally you will get this one with delta M1 dash M1 and delta M2 dash M2. So we can remove this, there is no problem. Now for writing the completeness relation with this equation, we have to take it the coupled state. So for writing that, J1 and J2 and M1 dash M2 dash, here I am J1 J2 M1 M2 is equal to delta M1 dash M1 delta M2 dash M2. So this completeness relation which we are going to write here is on the basis of coupled states, because we have taken the orthogonality condition with the uncoupled state. So in that case J1 J2 M1 dash M2 dash, so I am writing this one, so sum over M1 equal to minus J1 to J1 and sum over M2 equal to minus J2 to J2. Then here outer product between the two coupled states is J1 and J2, J3 M3. For this case what we have to write it, the M1 and M2 values are different. So J3 value, M1 is nothing but a J3, then here J3 moves from minus J3 to plus J3, and here this M3 value moves from minus M3 to plus M3. Then J1 J2 again J3 M3, then this term will come, it is nothing but J1 J2 M1 M2 is equal to delta M1 dash M1 delta M2 dash M2. Then again for rewriting this expression, so one can put it J3 equal to minus J32 plus J3, again sum over M3 equal to minus M32 plus M3, then J1 J2 M1 dash M2 dash, this term I am writing here, then this will come J3 M3, then here if you come J1 J2 and J3 M3, then J1 J2 M1 M2 is again delta M1 dash M1 delta M2 dash M2. Fine. Already I told that this is actually an inner product between these two states or a number or real value. Inner product between these two states are nothing but a real number. So we can actually rewrite this one instant of sum over J3 equal to minus J3 to J3 plus J3, sum over M3 equal to minus M3 to M3, then J1 and J2, you can actually interchange this state or you can interchange this state, there is no problem. So whichever the state you can interchange. So I am actually interchanging here. So J3 and M3, and if it is coming here J1, J2, J2, then M1, M2 dash, then you can keep this one as such. So J1, J2, J3, M3, J1, J2, M1, M2 is nothing but this one. So delta M1 dash M1, delta M2 dash M2. Fine. Further implying a condition, now for getting the normality, we have to write it M1 dash is nothing but M1 and M2 dash is nothing but M2. If we apply this condition, then we will get the normality condition. Okay, so fine. Now sum over J3 equal to minus J32 plus J3, and again sum over M3 equal to minus M3 to M3, then this one J1, J2, J3, M3, J1, J2, M1, M2. So double times, then this will be M1 dash is nothing but M1, then delta M1 M1 will be 1, again delta M2 dash M2 will become delta M2 M2, then this will be 1. This is the condition for getting the normality. Condition for normality. Fine. So far what we discussed, how to transform the uncoupled basis to coupled basis, vice versa with the unitary transformation, and that unitary transformation, that the coefficient of the unitary transformation is all or real number, and now we will see or the continue how to calculate that number with some selection rules. Okay, first we will discuss the selection rule, CG selection rule. There are two selection rules in this. So the first selection rule is nothing but M3 equal to M1 plus M2. That means the sum of two magnetic quantum number. So this one is actually M1 is the magnetic quantum number of the system belongs to Hilbert space H1, and M2 is the magnetic quantum number belongs to the state or H2 space, and sum of these two magnetic quantum number from H1 subspace and H2 subspace is nothing but the magnetic quantum number of the Hilbertian space H3. Fine. Now how to prove this? Okay, so M3 is equal to M1 plus M2. So where is the proof we have to discuss? For taking the proof, I am starting from the operator, this is actually the operator, and the angular momentum operator in z direction for the system 3 or the Hilbertian space H3 is equal to the sum of the angular momentum operator along z direction of system 1 plus the angular momentum operator J2Z is belongs to the second Hilbertian space subspace. Okay. Now take the state vector, the uncoupled state vector on both sides. Take the uncoupled state vector. Okay. So then J3Z, J1, J2, M1, M2 is equal to J1Z, J1, J2, M1, M2 state vector on both sides, then plus J2Z, J1, J2, M1, M2. Keep it this one because J3Z do not play any role on this state because J3Z is the coupled basis operator, but J1Z and J2Z are the uncoupled basis operator. So what is the result if J1Z acts on this uncoupled basis? What will be the result? So this will act always on this magnetic quantum number, and this will actually play with magnetic quantum number M2. Then we will get it here. M1 H cross is nothing but the eigenvalue when this operator acts on this state. You can say eigenstate. Then we will get eigenvalue with M1 H cross, and then eigenstate is M1 M2. So coming to the J2Z acts on this uncoupled basis or the eigenvector, then we will get it M2 H cross, again state vector J1, J2, M1, M2. If you take out the state vector M1 plus M2 H cross as this as a common J1, J2, M1, M2, we will get. So here J3Z is nothing but J1 and J2, M1, M2. Fine, you keep it this value. Now J3 operator is there here, J3 Z operator is there, and we are taking a coupled state. Suppose the J3 Z operator acts on the coupled basis only. So now we have to take it the coupled basis J1, J2 and J3, M3. So if this operator acts on the coupled basis, we will get it M3 H cross is eigenvalue and J1, J2, J3, M3. We will get this one. Fine. So finally what we can actually achieve it from this equation, if you look this equation, then finally we can achieve the value of J3Z is nothing but M1 plus M2 of H cross. So this will be removed on both sides. And also after this state vector acts on this state, we can also remove this state vector. So from here what we can get it, J3Z is nothing but M3 H cross. If you compare these two expression, one can easily write it M3 is nothing but M1 plus M2. So this is the first selection rule for transforming a coupled basis to uncoupled basis or vice versa. This is the first selection rule. Okay, coming to the second selection rule. So the angular momentum J1 and J2, if it is added, angular momentum quantum numbers, okay, the angular momentum quantum number. Okay, the second selection rule I am just giving you. The second selection rule is nothing but the value of J3 varies from the J3 value actually varies from J1 minus J2 and J1 plus J2. The quantum number value, when we are adding a two angular momentum, then the value of J3 goes from J1 minus J2 determinant value to J1 plus J2. This value will vary. So we will discuss proof of this second selection rule. Fine. So when we are adding the two angular momentum quantum number J1 and J2, we will get J3, and these J3 values, what are the possible values of J3 when we are adding J1 and J2? That's things. So J3 is nothing but a set of the value will go from J1 plus J2, then J1 plus J2 minus 1, then it goes to J1 plus J2 minus 2, it goes like until to reach J1 minus J2. So we can take it this as a J maximum, this as a J minimum. Fine. If that is the case, if n number of possible values J3, if it is having n number of possible values, then we can write it the number of element in this set, number of element in the set J3 or in the group J3 can be written n equal to sum over J maximum to minimum or J minimum to J maximum, whatever we can actually do it. So you write it J minimum to J maximum to J3 plus 1 will give you the total number of element belongs to this J3, or set of element of J3 can be determined by using this way. Fine. Now you apply the value of J minimum in the place of J3. So what will be the answer? 2 J minimum plus 1 or one can actually write it J maximum to J minimum. So that is no problem. It is very easy to understand and prove the theory. Okay, so make it like this. Then for writing this 2 J maximum in place of J3, you can write it J maximum and plus 1, then plus, make it bracket, then 2 J maximum minus 1 plus 1, again another bracket here, then plus 2 of J maximum minus 2 of plus 1, again another bracket. So it will go until so J minimum, so plus 2 J minimum is nothing but J1 minus J2, but I don't know what is the actual value. So now you keep it as J minimum plus 1. Then if we are expanding this term, so 2J maximum plus 1 plus here 2j maximum plus 1 minus 2. So if you multiply this 2 here, so you will get minus 2 here. Then plus 2j maximum plus 1. So 2 times you will get it 4 minus 4. So it will go like 2j minimum plus 1. It goes like that. Fine. Now the common difference between the final term to initial term, if you take it this as a final term and this as an initial term, then the common difference between this successive term or this term or the next to this term, the successive term will be minus 2, the common difference. So the difference is nothing but minus 2. Then the sum of the values or the number of the element n present in this expression can be written n equal to L plus A and L minus A plus D divided by a common difference D, 2D. So 2 times the common difference D. Okay. So here L is nothing but the last term. L is nothing but the last term of this particular series. Okay. Last term of the series, and A is nothing but the first term of the series, then the value of last term of the series is nothing but 2j minimum plus 1, and the first term of the series is 2j1 plus j2. This is nothing but a j maximum. So plus 1 is nothing but 2j1 plus 2j2 plus 1. If we feed this value, then the arithmetic progress n can be written in this formula, and last term 2j minimum plus 1, this one last term, and plus the A is first term 2j1 plus 2j2 plus 1. Complete the bracket. Then come to here, again last term 2j minimum plus 1, then negative sign, and then a last term minus 2j1 minus 2j2 minus 2, then plus D, the common difference between the successive term, in that series is minus 2, then we can write it minus 2 here, then divided by 2 times the common difference. So 2 minus 2, it will be 4. So we can write it minus 4. Fine. If we simplify this expression, and then put here this value of n in the previous slide we have discussed, the value of n is nothing but, this n can be written as 2 2z1 plus 1, this is multiplication, and 2z2 plus 1. Okay, so the number of element for the H3 Hilbertian space can be written, that's what it is written here. So H3 is nothing but H1 to H2, the number of element here 2j3 plus 1 is equal to 2z1 plus 1 and then 2z2 plus 1. Okay, so we are taking this one, it will give you the number of element presence in this Hilbertian space. So that's what I have written, it is equal to, this is equal to, then we can modify 2j minimum plus 2z1 plus 2z2, then you will get it plus 2 here, adding these two terms. By looking here, we can actually, so minus 2 and minus 2 here plus 1, then we'll get it minus 3. Minus 2z1 oh, here this is 1, that will be minus 1. So sorry, that will be minus 1. Then the plus 1 and minus 1 will get cancelled. So the remaining term 2z minimum minus 2z1 minus 2z2, then minus 2, we'll get minus 2. Divided by minus 4. Okay, so 1, 2 can be taken out from this common value, 1, 2 can be taken out from this value. Then if we take it a 4 out divided by minus 4, so we will get it z minimum plus z1 plus z2 plus 1, then 2 minus 2z1 minus 2z2 minus 1, sorry, this is j minimum minus j1 minus j2 minus 1. So we will get, here it will be minus 1, then this can be further rewritten minus 2z1 plus 1 2z2 plus 1 is equal to j minimum plus j1 plus j2 plus 1, then product with j minimum minus j1 minus j2 minus 1. If you short out this term, finally we will come to end up with j minimum squared, because if you multiply j minimum with j minimum squared will come. Okay, then other term you can actually short out. Finally j minimum square, just it is a multiplication and then rearranging the terms from right and left, that's it. So j minimum square, you will get it j1 square plus j2 square, then minus 2j1 j2. So this value is nothing but j1 minus j2 whole squared, or the j minimum value is nothing but j1 minus j2 determinant. This is the value for J minimum up to the difference of J1, J2 can go. Fine. Suppose J3 equal to J1 plus J2 is the maximum value, is nothing but J maximum value, and J3 if it is J1 minus J2 is nothing but J minimum value. So how to get geometrically this one? Suppose this is nothing but J1 quantum number and J2 quantum number is in this direction. If you take it, then the J3 quantum number having a 2 possible value, this one, look it, from this figure one can write it J2 plus J3 is nothing but J1. It is actually a triangular law of additions of vector, this one. Okay. So this one J1 will come. So what will be the value of J3 here? So keep it J3, J1 minus J2. This is what we are getting here. In another way, we can also write it this equation. Suppose if your vector is in this direction, of course this is J2 and J1 and J3. So if this is the case, then from this geometry one can write it J2 minus J3 is J1, or you can write it J1 plus J3 is nothing but J2. Or if you move in this way, if you move this way, then you will get this one. If you move again this way, then the equation can be written J2 minus J3, because it is in opposite to this one. So you will get it J1, and other words we can write it here minus J3 equal to J1 minus J2, or this case J3 equal to determinant of J1 minus J2. So that is the condition for getting the J minimum. So how to geometrically explain the additions of these two vectors J1 plus J2 will give you J maximum. Okay. For this condition, we can use the additions of vector by a parallelogram law. Then look at this is example J1 and J2. If this magnitude is J1, J2, then this magnitude is also J2. If this magnitude is J1, then this is also J1. If you want to get it the diagonal value of this parallelogram, this value, if you want to, this is nothing but a J3. So how we will get it? So first J1 plus J2, we will get J3, that is nothing but J maximum. And now one can also couple it here. If this diagonal will give you J minimum, now I am removing J minimum, and this diagonal will give you J maximum. J maximum. Either you can write it like this, or vector may be moving upward, it doesn't matter. Okay. This is the pictorial representation, and you have studied it, something called the triangular inequalities in mathematical physics, also that linear algebra. So it's also explained the triangular inequalities. Okay, fine. Now let us see how the CG selection rule. According to the CG selection rule, first rule, M3 must be M1 plus M2. This is the first condition. If this condition is not obeyed, then what is your system? How it would be the system physically? So let's see. For discussing this, you take it uncoupled basis. Suppose J3 is at, so this is nothing but the operator J3 operator acts on G direction, and you take it uncoupled basis J1, J2, M1, M2 here is nothing but, we have already discussed, J1 is at J1, J2, M1, M2 plus J2 is at J1, J2, M1, M2. We have discussed. You consider this one. Now rewrite this equation. J3 is at J1, J2, M1, M2 minus J1 is at J1, J2, M1, M2 and minus J2 is at J1, J2, M1, M2 is equal to 0. There is no problem. Now take this entire term with inner product of coupled state. This is uncoupled state. Okay. Now you take it the inner product of coupled state to this equation. Okay. Then J1, J2, J3, M3, J3 is at J1, J2, M1, M2 minus J1, J2, J3, M3, J1 is at J1, J2, M1, M2 minus again J1, J2, J3, M3, J2 is at J1, J2, M1, M2 is equal to 0. No problem. Here to this value, this J1 is at acts on this M1 magnetic quantum number M1. This will acts here, and this value though will acts on M2 magnetic quantum number M2. But when you come here, J3 Z will acts on coupled state, but this is not a coupled state, this is uncoupled state, so it cannot act on this one. So in other words, the J3Z can act on this way, but if it is acting on this way, then J3Z must be Hermitian. Okay, J3Z is nothing but J3Z Hermitian. If that is the condition, then no problem. So we can write it J3 transpose also here. If I am applying here transpose, then this state will act on this. If this is the state condition, then this will actually act in ket vector. But J3 is that if I am putting a transpose here, then this will act on a bra vector, and J3Z is nothing but J3Z transpose. So there is no problem. In that case, this state vector can be finally written as this one by adopting this condition. So J3Z transpose is nothing but J3Z. So J3Z. Now this will actually play with this magnetic quantum number M3. If that is the case, the final result, what we will get it here, I am writing m3 h cross, this is a eigenvalue when J3 is there acts on a coupled state. Okay. Then inner product J1 and J2, J3 m3, then J1 J2 m1 m2, this minus, of course this operator J1 is it acts on the m1 magnetic quantum number in the state uncoupled state, then m1 h cross, J1 J2 J3 m3, again J1 J2 m1 m2 minus, when you come here you will get it m2 h cross, J1 J2 J3 m3, J1 J2 m1 m2 is equal to 0. So definitely we can actually write it this equation as m3 minus m1 minus m2 of h cross J1 J2 J3 m3 J1 J2 m1 m2 is equal to 0. So finally we can reach to this point here. If you look carefully this expression, m1 minus m2 minus m3 cannot be 0. If this is the 0, then the entire term will be 0, then there is no physical meaning of doing this process, selection rule. Then it cannot be actually 0, but this can be 0. If this is 0, then J1 J2 J3 m3 J1 J2 m1 m2 is equal to 0. So inner product between any of these two states, if it is 0, that means it's a orthogonality condition. We are actually coming to the orthogonal state. These two states are orthogonal with each other. That means J1 J2, and that means this is a coupled state and uncoupled state. Okay, so these two are the orthogonal with each other. So this can be 0, but this cannot be actually 0. So if we want to find out the CG coefficient, states should be orthogonal with each other, whatever. So states should be orthogonal with each other. If states are orthogonal with each other, then we can actually get it m1 is equal to m2 plus m3 equal to m1 plus m2. We will get this term, this condition. Now let us see the raising and lowering operator when it acts on total angular momentum. For writing the raising and lowering operator, on total angular momentum J3 plus minus of H3 space, Hilbertian space. Now you take it, J3 plus minus is nothing but J1 plus minus plus J2 plus minus. One can write. By using the coupled basis, this equation further can be expanded. J1, J2, J3, M3 is equal to J1 plus minus J1, J2, J3, M3 plus J2 plus minus J1, J2, J3, M3. One can easily write. Okay, let me solve first this term, then we will come to solve this term. So how to solve this first term? It is a raising and lowering operator. Being a raising and lowering operator, it acts on always the magnetic quantum number in one notch either upward or one notch either lowering down. So if that is the case, then so if J3, if this is acting on this, we will get it J3 of J3 plus 1 minus M3 of M3 plus minus 1 H cross, then the state vector J1, J2 and J3 M3 plus minus 1 we will get. This is no problem. So now we come to write this one. So what will be the answer for this? Okay, we'll discuss J 1 plus minus plus J2 plus minus of J1, J2, J3, M3. I am solving the right hand side. Now J1 plus minus plus J2 plus minus, here I am inserting the completeness relation here, and then J1, J2, J3, M3. For solving this, we have to do like this. So J1 plus minus plus J2 plus minus. So what is the completeness relation with the uncoupled basis? Because it's here already we have considered it as a coupled basis. So in this case, for writing a completeness, we had to consider the uncoupled basis. So uncoupled basis sum over J3 equal to M3 equal to M1 minus J12 plus J1, then sum over M2 equal to minus J22 plus J2, then in this is an outer product. So J1, J2, M1, M2 and J1, J2, M1, M2, then this term is there. So we will continue with J1, J2, J3, M3. Okay. As I already told, this is nothing but an inner product between any two state is a scalar quantity. So instead of writing this equation here, this term, we can bring it from here to here. There is no problem. It's a number, so we can bring it over here to here. Then we are bringing this one from here to here. Yes. Sum over m1 equal to minus j1 to z1, and again sum over m2 equal to minus j2 to z2. Then you take it, this z1 z2 m1 m2 z1 z2 z3 m3, then z1 plus minus plus z2 plus minus this state j1 z2 m1 m2. Now this operator can actually act on this state, then you keep it out here. Sum over m1 equal to minus j1 to z1, and again sum over m2 equal to minus j2 to z2, then z1 z2 m1 m2 z1 z2 j3 m3. Here, when this operator j1 plus minus acts on this state, the magnetic quantum number m1 will actually move up or down one notch. Then j2 plus minus acts on this state, then this will actually play with the magnetic quantum number m2 one notch up or down. So in such a way, if j1 acts on this, then we will get it j1 of j1 plus 1 minus m1 of m1 plus or minus 1 under square root h cross, then the state z1 z2 m1 plus or minus 1 m2 will be there, then plus h cross j2 plus minus acts on this state, again we will get it square root of j2 plus 1 minus m2 of m2 plus minus 1 switch cross, then j1 z2 m1 m2 plus minus 1. So this is what the answer we will get it. So the completeness relation we can go with there's no problem, so we can actually write it in such a way. This is nothing but h cross j3 of j3 plus 1 minus m3 of m3 plus minus 1 under square root, then z1 z2 z3 m3. This what? This one. if we are taking m3 m3 plus minus 1, if we are taking inner product with uncoupled bases in this expression, further we take inner product with this state, so finally we will get I'm writing that equation J1 J2 M1 M2 J1 J2 J3 M3 plus minus 1. Take the inner product, then you divide this factor on both sides, then we will get it. Here is equal to h cross to will cancel, then J1 of J1 plus 1 minus M1 of M1 plus or minus 1 divided by this term J3 of J3 plus 1 minus M3 of M3 plus minus 1, then inner product J1 J2 M1 plus minus 1 M2 and J1 J2 J3 M3 plus minus 1 plus J2 of J2 plus 1 minus M2 of M2 plus minus 1, J3 of J3 plus 1 minus M3 of M3 plus minus 1, then here J1 J2 M1 M2 plus minus 1, J1 J2 J3 M3 plus minus 1. So when the raising and lowering operator acts on a coupled state, then the coefficient can be determined by solving this equation. Fine. So finally we are coming to list out what are the points to take care for solving the CG coefficient. There are certain points we have to take care. I am just listing out CG coefficient using sequential approach. So the first approach, first point, choose the values of J1, J2, whatever the system. So find it, the system's values of J1 and J2. Choose the values of J1 and J2. Total angular momentum quantum number J1 and J2 and generate all the possible values of J3. Now, the second point, generate all the possible values of values of magnetic quantum number associated with the total angular quantum number. So, possible values of J1 and J2. Possible values of J3. Values of J3 by using J1 and J2. Then for writing J3, A value, J3 as we already discussed under the selection rule, so J3 can go J1 plus J2 to determinant of J1 minus J2, that means J maximum to J minimum. So the values of J maximum to J minimum are the set of that values are J1 plus J2 comma J1 plus J2 minus 1, it goes until J1 minus J2 determinant. Then coming to the second selection rule is nothing but M3 value. So we have to list out all the possible values of M3. So M3 is nothing but a J3 and J3 minus 1, again J3 minus 2, it goes to minus J3. The values of M3 moves from plus J3 to minus J3. Here, say example, the J1 value is 1 and J2 value is 1 by 2. Then the possible values of J3 are J maximum to J minimum. So J maximum is nothing but J1 plus J2 is nothing but 1 plus 1 by 2 will be 3 by 2. Then J minimum is nothing but J1 minus J2 determinant. So J1 is 1 and this is 1 by 2, so total 1 by 2. Then the possible values of J3 here, so J maximum is 3 by 2, then 3 by 2 minus 1 if you one notch down. So you have to come from J maximum to J minimum with lowering one notch down. So if you are coming, so 3 by 2 minus 1, you will get 1 by 2. So only these two values are under J3. If this is the J3, then what is the magnetic quantum number for M3? Magnetic quantum number of M3. Suppose if you are considering J3 is 3 by 2, then the values of M3 is nothing but plus J3 to minus J3. So 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2 or the values of M3 magnetic quantum number with respect to the total angular quantum number. J3 is nothing but 3 by 2. And for the J3 1 by 2, then the values of M3 is nothing but 1 by 2 minus 1 by 2. Only two values. This is what this. Fine. Coming to the third point. Start with the state representation. Three. State representation by a coupled basis J1, J2, J3, M3 state representation. Here you take it the two conditions. A is nothing but m1 equal to j1 and m2 equal to j2. It's a maximum value. So for j1, the m1 is the maximum value, you consider it. For j2, m2 is the maximum value, so you consider it. For example, if j1 is 3 by 2, the possible values of m1s are 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. But you have to start with assigning m1 is equal to j1 or j1 equal to m1. Here this way, state vector j1 is nothing but m1, j2 is nothing but m2. Start from the maximum state vector, okay, to lower one notch down until to get it the j minimum, okay. So in that case you keep it this condition m1 equal to j1 and m2 equal to j2, and j3 value also should be the maximum. So you can go for m1 plus m2 or m1 plus m2, or m3 is nothing but j1 plus j2, of course, okay. So if j3 is equal to j1 plus j2, then if j1 equal to m1, j2 equal to m2, then j3 will be m1 plus m2. In other words, so m3 is equal to m1 plus m2, then m1 is j1 and m2 is j2, then this both the conditions are can be written j3 equal to m1 plus m2 and m3 equal to j1 plus j2. There is no problem for writing this. And what is the coefficient? You find it, the CG coefficient. So the inner product between the coupled and uncoupled state. So j1 j2 m1 m2 j1 j2 j3 m3. This is nothing but the CG coefficient, okay. So by using these conditions, whatever it is listed out here, so one can easily write j1 j2 j3, sorry, this m1 m2 again as j1 j2, then j1 j2, keep it. j3 is nothing but m1 plus m2 and m3 is nothing but, or if you are writing j3 as m1, sorry, j1 plus j2, then m3 is nothing but again j1 plus j2. Of course this will be delta j1 j1 and this is a delta j2 j2, so there is no problem. And here when you come again delta j1 j1 delta j2 j2, it will be 1 delta j1 and delta j1 plus j2 and delta j2 delta j1 plus j2. So you will get these two valid terms only. So this is a third point. And fourth point, apply the lowering operator on this state vector. Fourth, apply the lowering operator, use j3 minus lowering operator on j1 j2 j3 m3 is nothing but j1 minus plus j2 minus j1 j2 m1 m2. So j3 minus acts on this state, we will get it m3 h cross j3 of j3 plus 1 minus m3 of m3 minus 1 is equal to here H cross M1 J1 of J1 plus 1 minus M1 of M1 minus 1 J1 J2 M1 minus 1 M2 plus M2 H cross J2 of J2 plus 1 minus M2 of M2 minus 1 J1 J2 M1 M2 minus 1. Okay. So repeat this operator until to get J3, this quantum number here. Na? So J3 is nothing but the J1 plus J2, J maximum. Okay. And fifth one, repeat until to get until J3 equal to J1 minus J2. You have started from the most highest value of state vector. So from the top value of the state vector, you are coming down, one notch down, one notch down, one notch down, until to get J3 equal to J minimum. So you are starting from J maximum, and by using a lowering operator J3 minus acts on J maximum, then you will come one notch down, down, down again. So I am writing here. So J3 minus acts on J maximum. Okay, this is the state, the J maximum state. Then if this operator acts on this, I am writing this as a J maximum. Then if J3 minus acts on J maximum, you will come J maximum minus 1, one notch down. Again J3 minus acts on this state, then you will come J maximum minus 2. So until to get J minimum. So that's why, so repeat until the quantum number J3 to get it a J minimum. And if you are reaching J3 equal to J minimum, then the value of M3 equal to minus J3, because M3 value we have written it, the possible values are M3 is nothing but J3 and J3 minus 1, it will go until minus J3. So then M3 value will be minus M3 and M1 value is minus J1 and M2 value is minus J2. And the sixth point, take the orthogonal state. I'm writing that sixth point. So, considering J1, J2, I'm writing a state vector M1, M2, sorry, CG coefficient, then J1, J2, this is J3, M3 is nothing but CG coefficient, and we no need to bother about this one, but we will come here basically. So this is nothing but J1 plus J2, and this will be also J1 plus J2, this value. So in that case we can omit, simply we will follow this one, J1, J2, J1 plus J2, it is nothing but J3, and M3 is also J1 plus J2. Then J3 minus acts on this state, so I will get another state. So this J3 always play with the this quantum number J3 minus, then J1 plus J2 minus 1 comma J1 plus J2. This is the state. I am not repeating J1 and J2, I am repeating only these two quantum numbers. J1, if J3 minus acts on this state, it will play with this. No, it play with this M3. It play with M3. So J1 plus J2 minus 1. Then again, if J3 minus acts on this, again this M3 will actually reduce to one notch, J1 plus J2 and J1 plus J2 minus 2. So it will go like this. So finding the orthogonal state, looking now, J3 maximum may be 3 by 2, J3 max. So here it will be 3 by 2 and this will be 3 by 2. If J3 minus acts on this, then this will be 3 by 2 and this will be 1 by 2. So 3 by 2, 1 by 2. Then 3 by 2 minus 1 by 2, it will go. So 3 by 2, then if any state, it can go. Otherwise, once it is reached to J minimum, then it will be stopped. Then other J3 value, J3 having two value, suppose 3 by 2 and 1 by 2. Then if you are considering J3 3 by 2, then M3 value we are listing. So another J3 is 1 by 2, then for that case, here can go J1 plus J2 minus 1 comma J1 plus J2 minus 1. So these two states are orthogonal state with each other. So orthogonal state. Then if it is actually moving, J3 minus acts on this state, it will be J1 plus J2 minus 1 comma then J1 plus J2 minus 2. Then if we are moving one notch down from this, then this state is orthogonal with this state. Orthogonal with this state. So it will go like this. Orthogonal states will go horizontally and the lowering operator gives the state in vertically. This is a sixth point, and there is another point. Seventh one is we have to use the Gordan shortly phase convention. Use the content Hartley phase convention CSPS. So the first point under content shortly phase convention, if the value of m1 is equal to j1, then the CG coefficient is positive, and the B value, if j1 is greater than j2 and m1 is greater than m2, CG coefficient is also positive, otherwise it is negative. Okay. So how we will actually get it the positive CG coefficient, negative CG coefficient, we will discuss with one example in next coming classes. That's it.